So yesterday we had some technical difficulties, and so I'm going to just go ahead and record what I was going to do with you yesterday, and that is to introduce a rotational motion. And so this is anything that goes around in a circle, and we've played with this before. I mean, you took trig class, and so you know about the unit circle, right? So it's got a radius of 1 and doesn't have to have a radius of 1, but you start here and you move yourself around the circle, and you can indicate any position along this path by an angle. Oh, that just doesn't look great, does it? That's wonderful. That's supposed to be a theta. So it's basically one-dimensional motion with theta as the variable. I'm gonna have to put a theta in there that you can see. Okay, that's a lot better. So basically, we can keep track of angular position. Theta is angular position, and it will be measured in radians or rad or nothing at all. You see, a radian is actually a very interesting unit. Radian is a placeholder word for nothing, because a radian is created by taking the radius of your circle and laying it along the outside. And once you've gone r distance along the outside, that angle that you've moved through is called 1 radian. So it's the ratio of an arc length to the radius, so it has no units whatsoever. We just say radian as a placeholder sound for the unit, which is really that. Okay, if you take a time derivative or the slope of a graph of angular position, you're going to get angular velocity. And if you take, and that's going to be measured in radians per second, or actually just inverse seconds if you subscribe to the radians ain't no units at all theory. Put this over here. I don't like that pen. And then if you take another time derivative or the slope of that graph, you're going to get angular acceleration. And because you're moving around in a circle, there is some interesting stuff that happens. First of all, if you were to go around starting here at the kind of the home position and go around this circle and wind up back here, and if someone was to ask you your displacement, that would be your final position minus your initial position. But since they're both in the same spot, that would be considered 0 displacement in the rectilinear coordinate system. But in an angular coordinate system, you have gone through a full 2 pi here. So your finishing angular position is 2 pi, but your initial angular position was 0. So that is a displacement of 2 pi. So even though you're traveling along the same path over and over and over again, we continue to add to your angular position after each rotation, okay? Oh, by the way, angular acceleration would then be in radians per second squared, or just inverse second squareds if you are that type of person. The angular variables and the linear variables are related to each other. That is to say that if you take theta and multiply by r, you will get back your position. That's the distance traveled along the circle. If you take omega and multiply by r, you will get back velocity. And if you take alpha and multiply by r, you will get back acceleration. So these are related to each other. And if you don't remember what to do with the r, just remember that the units here are radians, and then we're going to be multiplying by r, which is in meters, and that's going to give us meters, which is what x is in. And similarly for the other ones, okay? Once you realize that these are the new things you have to keep track of, you realize that we can do exactly what we did before, which is to come up with equations of motion. So our good friend, the Swiss Army equation, xf equals xi plus vi times t plus 1/2 a times t squared, becomes theta f equals theta I plus omega I times t plus 1/2 of alpha times t squared. So there is an angular version for each linear formula. The definition of velocity becomes that. The no T equation, this one looks really cool. Two alpha theta. Kind of looks like a fraternity or sorority you might join. And then finally, what's that last one? The no X equation. That says that xf minus xi equals 1/2 Vf plus Vi times T, and that becomes theta F minus theta I equals 1/2 omega F plus omega I times T. Notice that T doesn't change in the angular world, it's still time. So these are the equations of motion if you're going to solve problems in a round and round sense. Okay, that brings us to the next thing that we would want to do with rotational motion, and that is, what was the next thing we did with oh, we did forces. Okay, so what are rotational forces? They're called torques. A torque is a force that causes twisting. So a torque can be a linear force, but then if something has a pivot point, then you're going to twist it. For example, the doorknobs in my house have this kind of a look. They have a round part, and then they have a handle that goes out like this, something like that. It's a lever-style doorknob. When we had cats, I actually had to put all the lever-style doorknobs hanging down because the cats learned to put their paw up and open doors and get in and out of places they weren't supposed to. But when you use such a doorknob, generally what you do is you exert a force downwards, a linear force at the end of the handle, and that causes a spinning of the handle because there is an axis of rotation right here. Now, axis of rotation, I like to use this symbol. It's a circle with a and that's slightly different but related to the symbol I use for center of mass. And sometimes they're the same place, you know what I mean? A lot of times things rotate around their centers of mass. Well, not this doorknob because it's mounted on an axle that goes through the door and also works the mechanism. So that force is going to cause a twisting. So how much torque is abbreviated with this letter tau, and it's for torque, and torque is equal to R cross F. R is how far away from the axis of rotation that the force is applied, and F is the amount of the force. Now this cross is a special vector thing called a cross product, and what it does is it honors the fact that there should be a right angle between these two things. So if you don't quite get a right angle between them, what you can do is you can take R times F times the sine of the angle between them. That's a cheap and cheesy way to get the cross product going. The actual thing you have to do with this cross product is you have to move your hand from the R direction to the F direction. And if you use your right hand and you move your right hand from the R direction, see my fingers are pointed that way, and then I'm going to move them down to the F direction, which is, oh, this hurts me to do that way. You'll notice that my thumb is pointing into the page. That means that this torque that's created by this force has a direction directed into the page. And that will tell you if a torque is directed into the page, then it's going to go clockwise. If a torque is directed out of the page, it's going to go counterclockwise. Again, whatever your fingers can do. So if it's directed into the page, your thumb goes down this way, your fingers can only rotate that way. Okay, so that's fun. We'll let that go. By the way, about tau. Tau is just a kind of a T. You can just make a T with a curly top, or you can make a straight top and a curving bottom, which kind of looks like a backwards J, or you could just go totally ape crazy like I do and do a curly top and a curly bottom. That lets me know that this is a tau and not a T. T is for tension, tau is for torque. So torque is a force that causes rotation. And it's made up of a force and the distance away from the pivot point that you exert that force. And that's why these kinds of doorknobs are better. If you're carrying something, you can just use your elbow and push down, or your knee or what have you. Now, in the world of linear forces, we said Newton's second law, F equals m times a. So you would think that we would say, hey, tau equals m times alpha. But that is not true. It's not just m anymore. When we're spinning and moving things around in a circle, the mass alone is not the most important thing. What is important is the moment of inertia. And the moment of inertia is a it is a calculation, much like the center of mass, that adds up for every bit of mass. Where is it located? The moment of inertia, the basic definition, is the sum of all the individual bits of matter times how far away they are from the axis of rotation squared. So actually, technically, in the world of mathematics, this should be called the second moment of inertia. And center of mass is actually the first moment of inertia, because the distances are not squared in here and the distances are squared in here. So you can actually calculate moment of inertia for some simple objects. And we're going to go through how to calculate a moment of inertia for more complicated objects. That'll be the next video I put out. And this turns into an integral if you have a continuous object. So we would then be integrating r squared dm. Now, this is a bit of a pain in the butt as an integral, as I mentioned before, and I'm going to say it again so that it seeps into your brain. This is a very annoying integral to do because we're integrating over the individual slices of mass, whereas most people are more comfortable integrating over spatial variables. So this is where we'd want to use the density trick to change variables. We'll do that, and I'll show you how that works when we move on. Okay, so a torque is a force that creates a twisting, and the torques, where is it? This is the one. This is Newton's second law for torques. They cause angular accelerations, just in the same way that linear forces cause linear accelerations. Well, let's move on. If we did forces, what was the next thing we studied? Oh, yes, I know. We studied energy. And so we're going to have rotational kinetic energy. So there's kinetic energy of translation. That means linear motion. And now we're going to have kinetic energy of rotation. Circular. And yes, an object can actually have both. Like a pool ball rolling down the table will be rolling, rotating, and moving sideways, translating. The kinetic energy of translation, of course, is 1/2 mass times velocity squared. So let's see if we can do this by analogy. Kinetic energy of rotation should then be 1/2 moment of inertia times omega squared. And that's indeed exactly what it is. Now, remember that moment of inertia is made up of masses and distances, positions, and that omega is made up of velocity divided by radius. So we could actually, every time we write this down, we could actually start substituting in linear variables if we happen to know them. I'm sorry, I'm covering up my work here. We can substitute linear variables in here, and we do that quite often, especially when you have both of these terms mixed together. Okay, so a ball that rolls down a ramp and starts at the top, and then as it gets towards the bottom, it is not only moving but also rotating. We would say that the potential energy it has up here turns into a sum of kinetic energy of translation and kinetic energy of rotation. So that's how we would solve that problem. And then we would have both of these terms added together, and mixing your linear and angular variables is a way to get a headache in a hurry. So we wouldn't want to do that. Okay. Again, this requires us to find this moment of inertia. So that will be an important part of what we learn how to do after winter break. And so finally, we get into rotational. Pardon me for a second here. Okay, sorry about that. I'm going through a process of harassing sales calls. Okay, rotational momentum is the last thing that we need to discuss. So, also called angular momentum. In fact, more often called angular momentum than rotational momentum. And in this one, we had our good old friend, momentum was just mass times velocity. So I guess if we were going to do this correctly, we would say that angular momentum, which gets the letter L, capital L, I like that because it makes an angle, it would be I times omega. And it is indeed I times omega. That is as simple as it is. However, it's kind of interesting because in the same way that momentum was conserved, P total equals P total prime, we have that L total equals L total prime. And this thing is really, really, really powerful. In fact, it helps explain stuff like why an ice skater who has his or her arms and legs out. So I'm going to try to draw a human body with arms and legs out. One leg has to be down on the ice, and then arms outstretched, and maybe moving a little bit or maybe rotating a little bit. But then when he or she pulls their limbs together and puts their feet together and crosses their arms over their body, then they will spin much faster. This will be a rotation that's really fast. So this person with their arms and legs out has a very large moment of inertia, but maybe a small angular speed. And then when you tuck your arms and legs in, you make yourself have a small moment of inertia, so you'll have a tremendously large angular speed. I'm sorry, that's a little low on the page there. So this is the trick for how to get yourself spinning really fast. You have arms and legs splayed out and a small amount of rotational motion. Start a little bit of a turn, and after you start that turn, you tuck everything together and you rotate quickly. All right, that's what I wanted to talk about today, and so that's going to constitute today's lecture.